Hi, everyone. Welcome to another informational webinar for DOE Energy Innovator Fellows. Today, we're really lucky to have Cody Davis from Electric Power Engineers, who does a lot of our training and helps us with technical assistance and research on distribution system planning and related topics. So today, he's going to cover operations, which is a really important topic for every single regulatory commission in the country, all of the electric utilities in the country, and all the stakeholders that engage with utilities and state regulators. Cody is a through and through power system engineer. He's got practical experience working at Ameren, Illinois, and he today works with a wide range of clients, including Berkeley Lab, utilities, and stakeholders on a variety of issues related to distribution planning and integrating distributed resources on the distribution system. So we're going to take your questions in the chat box at any time. I'll be looking there, flagging them for Cody. Feel free to raise your hand if you want to ask your question live during his presentation or after, and we'll call on you to unmute yourself. We have several webinars coming up. Next is on electricity markets, and that's going to be great for folks trying to understand how do things work in restructured states or mixed states. You might still have vertically integrated utilities, but have regional power markets. So P. Cappers is going to talk about that. Then we have Paul DiMartini with Newport Consulting Group. He does a lot of our training and helps a lot with technical assistance. And he's going to talk about the kinds of tariff provisions and distribution operations requirements you can put on distributed energy resources. So they're really useful for particular places and particular grid services on the distribution system. And then we're going to have scheduling probably second week of August. Natalie Mims-Frick with Berkeley Lab is going to talk about updated practices. We're doing some research right now. What's the latest and greatest on stakeholder engagement for stakeholders in distribution system planning? And we're also going to have peer sharing breakouts so you can hear from each other. We're also working to schedule two more webinars in May and June. One is going to be about cost of service studies, which are the basis for cost allocation across customer classes in rate making. And another one, more of a deep dive on demand flexibility programs and rates and how you actually do some analysis on load management. All right, I think that's it. Cody.
All right, awesome. Well, let me get this up and going. All right, how does that look?
Looks great.
All right, fantastic. Well, thank you guys so much for having me on today. Happy to be here and talk power. I can talk power systems pretty much for hours and hours and hours and hours. So today we're going to be talking about electric utility distribution and operations, and just sort of giving a lay of the land of the different roles, responsibilities as it relates to operational folks, engineering folks, and some other just sort of utility landscape, including what they do, how they do it, and how it all kind of works together. So we'll start with just like an overview of roles and responsibilities. We'll look specifically at the functions of distribution operations and distribution engineering, and then cover some emerging topic areas that are sort of changing the way that these groups interact with each other, and the ways in which everything's becoming more complicated and more interrelated. So starting off, distribution utility roles and responsibilities, I think it's useful to break it down by sort of essential utility functions. So the first, we have sort of the build and run the system folks, which are your operations. This is things like responding to outages, constructing new facilities, making sure that workers are safe when they're doing either of the first two things, and just sort of generally running and overseeing the system as it is and as it sort of functions on a daily basis. The second group of folks is my own cohort, the engineers. This is the folks responsible for generally investing in planning and designing the system. So the operators kind of get it as it is. The engineers sort of identify and correct and maintain and make changes, right? So we're making investments, we're changing, we're building the infrastructure so that the operations folks can actually construct the things and then run it. And then finally, customer service is an important dimension here as well, coordinating with customers. This is things like call centers, billing, service reps, key accounts. And then there's your sort of generalized support personnel that support and keep everything running sort of together, IT, regulatory, project management, et cetera. We're going to look primarily at the operations and engineering arm of this just because I think it's the most opaque. Most people, when we say, oh, that's customer service, they kind of have a good understanding of what that is. So we're going to dive specifically into the first two. So in terms of like personnel groups under operations, there's a couple of useful sort of subheadings to look at. The first is what we call like a control center or the dispatch. Dispatchers are the ones sitting at air quotes the desk and are monitoring and controlling the actual system. They have displays. This is when you see people in like movies or TV that have like 8 monitors all fanned out around them. Those are your system operators, dispatchers. You also have operations system support folks that help sort of implement and maintain a lot of the complex technologies that make the control center able to function. These are your SCADA, so supervisory control and data acquisition, so all of the data that's coming in from all of your end devices and substations. And then more recently, things like advanced distribution management systems, ADMS, the sort of brain layer that sits on top and can actually execute some controls and monitor things on its own. So that's sort of the function of the control center is to watch everything, maintain, and take some corrective actions. Then you also have the sort of regional operations folks that are much more sort of build and sort of patrol, right? So you have first your trouble trucks. There's a bunch of different names for trouble trucks. Generally, it's like a one-person truck that's out there responding to small outage events, performing routine inspections when there's not outages in their territory, making minor repairs, just sort of checking on things, and following up on customer calls. You've got line crews, which are your actual people doing the construction of the facilities and making major repairs. See kind of pictured here on the right from Portland General's Electric's website, what a construction crew looks like. We've got a nice bucket truck up there with the guy getting up pretty high, sort of just building and again, sort of maintaining um, the system when there are major elements that need to be changed. Um, we have substation maintenance in here, which kind of gets its own category because of how complicated and expensive substations are. They are responsible for inspecting and repairing substation equipment, sometimes doing substation switching. And then your sort of operations management layer is sort of coordinating the trouble trucks, the line crews, in some cases substation maintenance, along with the dispatchers to make sure that everything is functioning how it's supposed to. So these sort of people all together make up system operations. We've got a lot of linemen in there. We've got operators. We've got the sort of out operations management. On the engineering side, we've got a number of different sort of headings for types of engineers. Some of these overlap or are sort of shared duties or have kind of weird lines of demarcation. I'm going to call them out here separately and then kind of lump them back in together a little bit as we get towards the end. So one type of engineering is system planning. This is trying to make sure that you have sufficient capacity to serve new load connections coming in and maybe perform different types of system studies. This can include like DER interconnections for new like natural gas gensets, solar, battery storage, flexible loads, EV charging. All of your sort of major changes usually come through planning. Um, Asset management is another aspect here that is sort of focused on the condition of the existing equipment and sort of the process of making investments. So you're coordinating different types of inspections, capital projects to replace equipment, sort of maintaining a hierarchy of what kinds of upgrades you want to make on the system and sort of the relative value of some of those upgrades. We have a reliability engineering arm, which generally focus on is on reliability, usually looking at like outage statistics, responding to like requests if customers have high levels of outages that get detected, reviewing outage data to make sure it comes in as correct. Um, we have a DER integration group that generally manages like a DER interconnection process and performs some of the screenings and studies. In some cases, this is its own sort of arm of the organization, separate from planning. In other cases, the planning engineers are the ones actually doing the studies. There may still be a different sort of DER integration team to just sort of manage the process tracking or like customer interactions. So the actual work here can be divided a couple of different ways. Another group here is the design folks. These are the ones actually sort of developing construction drawings. This is people who make the packets that get handed to the linemen to go out and build it. Those are your designers. System protection is another one that you'll hear. These folks are responsible for coordinating different protection devices, generally making sure that when bad things happen on the system, it gets isolated and protects the system and the public as quickly as possible. And we'll get into a little bit more of that here in a bit. And the last one is kind of a catch-all, regional engineer or field engineer, division engineer basically handles some or all of the responsibilities of all of these other groups within a specific geographical area. This is how I started my career. I had about a couple hundred square mile service territory in around the Peoria area that I was the planning engineer. I did all the DER studies. If there was reliability complaints, they came to me. I did design. We did some protection stuff. But we also had specific groups that also did all of those things, but the more complicated version of it or the sort of substation version of it. So these are all relatively fluid. You'll see different organization structures and different levels of hierarchy across different organizations. Generally, larger utilities centralize a lot of this, so they'll have a more centralized planning group and put less emphasis on some of that in like the regional folks. But that's not ironclad either. So there's a lot of room for where these roles might move. Okay, so talking about sort of the primary functions of operations. What does operations actually do? Thing number one, outage restoration. So what is an outage and how does it actually get caused? Outages are caused by faults. These are unintended electrical contacts, generally resulting in really high current that can damage equipment. So tree falls across multiple energized lines is sort of a classic example. Protection devices exist to detect faults and disconnect the portion of the system that is experiencing that fault from the rest of the sort of healthy system. So this is accomplished by physically making an open point and disconnecting that section of the system. So we have a couple of different technologies that can do this. We have fuses, which is sort of pictured there in the middle. There's a fuse link inside that little barrel. This whole assembly is called a fuse cutout. What happens is when there's a fault, the fuse blows and that barrel will physically swing down in an arc to indicate that something bad has happened downstream of that device. So it helps people kind of troubleshoot. We also have reclosers, which are have multiple operation cycles. It can detect a fault, open itself, and then it recloses back in to see if that fault is still present. And if it is, it'll open again. If the fault is gone, however, it'll remain energized. So if you had a temporary fault that's not there anymore, if the tree branch kind of fell off after it got toasted, then it'll kind of keep everything energized. And then the third category, like circuit breakers, these are relatively heavy duty substation devices that are relay controlled. They can also do reclosing, but are just a little bit beefier and sort of more not really suited for mounting on top of a pole. When we talk about outage restoration, the goal is to remove the source of the fault if it's still there, and to re-energize our customers that are affected. Routine outages are generally handled by trouble trucks. So if you have a squirrel gets on a transformer and the fuse blows, they're the ones going out there identifying, yep, we had a squirrel, and throwing the fuse back in to re-energize. For large scale outages that involve a lot more damage, you may have dispatch involved. You will probably have the operations supervisor and crews as well. So now we're going to look at what that process flow actually looks like for an outage. So we have our fault that occurs. I've got my fault lightning bolt over here. My protective device disconnects the entire faulted area downstream. So in this case, it's a fuse. The outage gets detected by one of a couple of different means. Either customers can call in and say, hey, I'm out of power. This is the way it used to work up until we had better sort of smart metering technology. Um, Now with like AMR or AMI meters, it can send what's called like a last gasp and say, hey, I saw a power outage, come help me. Or you may be able to see some of the outages directly through like SCADA and utility telemetry. But once we know that the outage exists, The trouble truck is the one who responds and kind of patrols the area that's impacted. If there's no permanent damage, usually the trouble truck is the one who can restore power, again, by replacing a fuse or throwing a recloser back in. If there is repairs needed, usually you're getting a line crew. So you have an operations supervisor who calls a bunch of different linemen to make a crew, and then the crew assembles and goes out and makes those repairs. Operations is also responsible for worker safety, which is one of the most important aspects of like dispatch and an operations supervisor's job. Construction can be performed with equipment still energized. It can be de-energized, but it doesn't have to be. And there's unique precautions that you have to take for energized or de-energized work. So if you're doing construction with the system still hot, um, obviously you need to take precautions. So the first is that reclosing has to be disabled. The idea is if you have a person who makes electrical contact, you do not want to open and disconnect it and close back in on them. You want it to be like, whoa, I got to get off. I'm not going to try and reclose. It also trips generally a lot faster. This may be referred to as a hazard or like a one-shot mode on the recloser. Um, for energized construction, line crews are also using insulated tools. They're using like cover up insulation, which is pictured there on the bottom. And if they're doing like a pole replacement energized, which is a thing you can do and happens all the time, they'll use what's called hot arms, which are those little yellow fiberglass things off to the left and right on this pole to physically move the conductors out to either side to give them enough space to work in the middle so they can raise the new pole, transfer everything over, take the old pole out. So a lot of construction that happens energized because taking an outage is always a bad thing for customers and try to avoid that whenever it's feasible to do so. When it's not feasible, when you're working on things that are de-energized, the idea is to prevent them from becoming energized on accident and to make sure that if they do, that there is no sort of risk to the people who are doing the work. So this is accomplished by establishing where your your open points are that are not connected to the system and physically placing a lock on those switches. The crew also generally installs temporary conductors referred to as grounds between the energized phases and the neutral so that if it does become re-energized, it will immediately trip and fault, and all of that fault current will pass through the grounds and not through the people who are doing the work. A philosophy that you hear a lot with energized work or for de-energized is observe, test, ground. What that means is when the crew gets out there, before they do any work, they're supposed to look and make sure that things look like they're dead, that any um, like grounds that are supposed to be in place are already in place, or any open points that are supposed to be open are actually open. They'll do a test to make sure that the conductors aren't actually still energized, and then they'll place their grounds. And that helps to protect them and adds an extra layer on there. And then again, reclosing, switching, and these sort of locked open points are all controlled by dispatch. That is one of their functions is to sort of track, maintain, and ensure worker safety by controlling those points of worker protection. The process for doing line construction on energized lines, once you have sort of your engineering design completed, it goes to an operations supervisor who will review the job and request worker protection. So a hazard on a recloser, or in this case, it's energized, so just a hazard. Dispatch will review it, approve it. A trouble truck or a system operator will be able to set that hazard mode. So it'll physically get changed either in the field or remotely via SCADA. The construction gets completed and then that hazard gets removed. So that's sort of the general process flow. System optimization is another important and becoming more important aspect of operations. Modern operations is supposed to manage a lot of these sort of advanced optimization tools that are intended to improve performance and efficiency and restoration. Your advanced distribution management system is a sort of common platform to coordinate different types of system equipment like capacitor banks, regulators, reclosers, circuit breakers, etc. Um, the two kind of lead applications of this are voltage optimization and Flizzer. Voltage optimization aims to coordinate like cap banks and regulators to reduce the number of voltage violations and improve system operating efficiency. This is sort of a combination of two different concepts, conservation voltage reduction, which is the idea that at lower voltage, things operate more efficiently. So lowering the voltage is part of optimization generally, and then volt-var optimization, which tries to reduce the amount of reactive power flow through equipment and sort of reduces the losses as a result. So that's voltage optimization, and it's an application that can be run through this ADMS. The second one is FLISR, which stands for fault location, isolation, and service restoration. Kind of goes through where is the problem, how do we separate the problem from the rest of the system, and which portions of the system can we still restore without getting them into the fault. And I'll show an example of this a little bit later on. But that's its sort of goal is to coordinate the switches and protective devices to restore customers automatically when they can do so, and they're not impacted by faults. All right, so that's kind of a high level overview of system operations and what they do and sort of what their purpose is. Next, we're going to go through a little bit on the engineering side. So a couple of different elements of distribution engineering. The first we're going to look at is identifying grid needs and solutions. This is a relatively broad activity across a bunch of different dimensions. I'm going to segment it out by sort of my three big elements, which are reliability, capacity, and asset health. Reliability reduces the frequency or duration of outages. Capacity is the ability to accommodate new loads or interconnections. And asset health is the ability to keep things running without equipment failing due to age and condition. Um, so how do we identify grid needs for reliability? We're tracking metrics and outage data, things like SAIFI and SAIDI, which are metrics for tracking the frequency and duration of outages, either at the system level or on individual feeders. There are mechanisms like worst performing circuits that sort of classify which circuits have the worst, air quotes, worst reliability, like the worst 5% of circuits for SAIFI, are sort of metrics for doing that. Um, Grid needs for capacity are generally identified through like forecasting and modeling. So these are your interconnection studies, your power flow analysis, contingency studies, like load growth projections and forecasts, et cetera. And then on the asset health side, these are generally outcomes from inspections and just records and record keeping. So you may have pole inspection programs, transformer oil analysis, dissolved gas analysis, different types of sampling to just sort of check on where assets are in their life cycle. There's a bunch of different types of solutions to all of these problems that can come up across these. I'm not going to go through all of them, but we have kind of a good mix of different levels of complexity, of cost. Reliability has lots of options, mostly tailored to what the specific problems are. You can build new circuit ties to help sort of re-energize customers faster. You can do tree trimming and undergrounding. You can do animal protection. You can build a new substation. That's a reliability investment. Lots of different things impact reliability. On the capacity side, generally we're either upsizing existing equipment, replacing equipment with larger conductor, or like adding a new feeder, a new substation. You may also consider things like non-wire solutions in there, or just sort of general like phase balancing ways to sort of extend the life of your existing equipment. And then on the asset health side, the most common method is just replacing the thing that's too old to continue functioning. But there is also an element of considering different types of environmental risks here as well. For example, like a flood risk is one that's emerging as an asset health consideration. If a substation is located in a floodplain, like that's a problem, right? It doesn't matter if the thing is 10 years old, like that's an asset health risk that needs to be addressed. So there's a lot of different ways of kind of going about solving these needs. Most projects do at least one of these. Most of them do more than one. Okay, I'm going to dig in a little bit on the asset management side. So asset management, the goal is to efficiently utilize your equipment that you already have. This is maximizing the life of the asset and sort of getting as much out of it as you can, but stopping just short and making sure it doesn't actually fail in while it's energized. So generally, you're trying to stretch but stop short. There's a lot of different ways to accomplish this. The process flow here on the right, I took from Ameren, Illinois' 2025 grid plan. Generally, you are collecting data about those assets from a bunch of different types of sources. You're analyzing that data to try to predict how much life is left on the asset. You're feeding that information into algorithms, dashboards, workflows to make decisions about which ones to replace. And then you're actually taking action to replace those assets and then sort of enrolling them back in the tracking process from there. That's sort of how the life cycle of asset management and asset health really works. Asset management also ends up being the department that has the keys to the kingdom in terms of spending most of the time and is responsible for getting the most out of any capital investment dollars that come through. I'll call this portfolio optimization. There's a bunch of different departments that all need different things. Asset management is usually the ones deciding which of those are most critical and most valuable to the business and to the customers, and going forward from there. Asset management also develops and manages like new and existing programs to address recurring issues, hole inspections, animal guarding, that kind of stuff. So they have a pretty broad mandate to just sort of generally manage the assets. The grid is mostly assets, so this is a huge, huge aspect of grid engineering. All right. And then the last piece, engineers are also operations support and help engage in grid modernization. That's the subheading for my title is grid mod. So this is an area I do a lot of work in. What does that actually mean? On the operations side, a lot of times you're doing studies for switching to see if certain types of reconfiguration on the system are practical. So if we need to take a substation transformer out of service for maintenance, how do we restore all of the customers that are normally served by that station? And can we pick them up from other places? That's a switching study that a planning engineer might do on behalf of operations. The other thing is to help sort of evaluate and deploy new technologies and new hardware to improve grid operations. So I mentioned voltage optimization and Flizzr earlier on. On the right here, we have kind of an example of how Flizzr actually operates. So we've got two feeders, feeder one on the top, feeder two on the bottom. And the top one is the top set of feeder one and feeder two is the before, and the bottom part is the after. So we're going to introduce a fault here just outside of the exit of feeder two, and that's going to de-energize all of those sections with the red X's between the feeder two and that T1 normally open tie recloser. Well, I've got these two other reclosers here, R1 and R2, that I'm calling midpoint reclosers. So what Flizzr is going to do is identify that area between R2 and T1 is out, but there's no fault there. So I can actually take that R2 recloser and open it, and now I've got my fault isolated between the feeder 2 exit and that R2 recloser. And now I can close T1 to re-energize all of those customers between T1 and R2. So the idea is those customers are out because of an upstream issue, but we can reconfigure the system to get them back on without having to make any repairs. And it dramatically increases the speed of restoration to at least some of the customers who are impacted, which is awesome. Op support also involves like grid modernization, like new technology, new hardware, looking for places to add new capacitors or regulators or reclosers to improve the performance of these systems, as well as tracking different types of performance metrics around how well like Flizzr is doing outage prevention, what sorts of metrics are coming out of that, and where you can make changes. Okay, so those are kind of a broad overview of operations and engineering. You can kind of see them
But
coming together already.
Cody,
Oh,
let's
go ahead.
break for a question here.
Sure.
We've got a question from Lucas. I'm not an electrical engineer by any means, but can you speak to what sort of controls distribution operators have for voltage optimization? And what kind of variables are they working with to achieve the efficiencies they're aiming for?
Yeah, that's a great question. So when it comes to managing voltage, we have two major tools. We have voltage regulators and capacitor banks that have different but related functions. The voltage regulator is functions similarly to like a dimmer switch on your like lights. So if you have your like voltage all the way up, you can dial it down in steps with a voltage regulator. It will physically retap so that it adjusts the downstream voltage. So if you've got Let's say you've got 120 volts coming in and you want to lower that to 118 volts. You can install a voltage regulator there and it will make that change. Similar, operates on the same principles as a transformer, but a different execution in practice. Um, Operators with for voltage management can see and actually change those ratios from the control system. So they can see the voltage coming in, they can see the voltage going out, and you can like change that tap in real time. So if you said, I want to increase my voltage by 5%, I can physically make that adjustment in the operating room, and it will send the command out to that end device. We also have capacitor banks, which are more complicated to explain, but reactive power generally is bad. It's the imaginary component that comes from magnets. Um, the more reactive power you have in the system, the more losses everything experiences, the more voltage drop that you have, and it just generally is more inefficient. Capacitor banks offset that. So you can physically control whether they are connected or disconnected to help balance your power factor and bring it as close to like zero reactive power flow as you can manage. And operators can physically turn those banks on and off with switches from the operations room. So those are the sort of inputs. In terms of variables, usually what you're trying to achieve is efficiency, so less losses on the system, less energy burned away due to heat, as well as usually you're also trying to reduce the operating voltage because it helps customer equipment operate more efficiently. So hopefully that paints a decent picture of what's going on.
Thanks, Cody. Does anybody else have any questions? You could take yourself off mute and ask, or you could put it in the chat before we get on to emerging. And there'll still be time at the end for additional questions.
One question, how different is all of this operations for like high voltage transmission systems? And I guess what would be the major differences?
That is a great question. There's a lot of similarities between transmission and distribution, just sort of structurally. The biggest difference is in like scale and criticality. So they deal with much, much higher voltages. They deal with much, much more dangerous situations for worker safety. It's more complicated, but a lot of this is the same, right? Transmission operations is still responsible for like determining where crews are working and making sure that they are working safely and applying like open points and everything. Um, they're also doing a lot more sort of contingency planning. So if you have like a loss of an individual line, that's something that they are much more sort of automatically prepared for. Structurally, they're very similar, but the transmission side is just sort of scaled up due to the cost and complexity. There's also a lot closer integration between like generation resources and transmission operators because of how like inherently intertwined those two things are. Whereas like distribution operators almost never see or interact with like generation resources in any real meaningful way. So that coupling is a lot tighter between transmission and generation. But other than that, it's the same general sort of approach. It's the same monitoring, um, more complicated systems, but the same sort of underlying goals.
Thank you. I know that's not the topic of the talk today, so I appreciate that.
Yeah, of course.
Anybody else have any questions before we move on to emerging areas?
I guess maybe just to follow up on helpful answer you gave on that voltage control. I guess I'm still trying to wrap my head around like what a distribution kind of control center person is doing sort of on the day to day. Like how what sort of controls are they working with and how are they influencing the system beyond responding to maybe like an outage or those type of scenarios?
Yeah, for the most part, the most common thing that they do is open and close circuit breakers and reclosers remotely for like restoration. So if they can reconfigure things to like move load from one device to another device so that like it can be taken out of service for maintenance. That's like the most common thing that they're actually sort of changing on a daily basis. A lot of the like process here is like managing all the requests and just sort of watching like who's getting access to do work and so that it can be done safely. So like coordinating, making sure that like a hazard got placed before a crew goes out and does work, um, that kind of stuff. So it's a lot of overseeing. With the voltage optimization piece specifically, most of that is happening automatically with the software. They have sort of manual capabilities with it, but they're not really touching those buttons unless something goes really wrong. They can go out and change voltages. They can adjust like capacitor banks, but for the most part, they're not doing that on a daily basis. Like very rarely, if ever. They are mostly focused on worker safety and outage restoration.
Yeah, that's helpful. Thanks.
Mhm.
All right, we can move on to the emerging areas and we'll come back for questions at the end as well.
Okay, awesome. So in terms of emerging focus areas, the biggest trend is just the breakdown of these silos. You'll see this a lot. You'll hear it talked about a lot. We're doing better. There's still a lot of silos, but the idea is that we're all getting sort of pushed to work more closely together with folks who are different than us at the utility to get things done. And this is across a couple of different ways. But historically, everything's operated like relatively independently, and that's starting to change more and more every day. This makes everything more complicated. There's new technologies, there's higher expectations that are really driving these. So we're going to look at three examples of these sort of silos breaking down and how and what that means. We're going to look at flexible interconnection, we're going to look at resiliency planning, and we're going to look at proactive investment. Okay. So flexible interconnection is this sort of intersection of planning and operations. Historically, load and DER interconnections are planning's purview. They do the study, excuse me, they study it kind of as it is, and it gets connected and it operates, and operations never actually sees or touches it. They just see the little numbers go up when more load or more DER gets added to the system. This is sort of a set it and forget it mentality. You do the study, you fix anything that needs to get fixed so it can connect, and then you plug it in, and operations doesn't have to do anything. Um, that's changing. Flexible interconnection is driving some of this. There are sort of a difference between these sort of static methods and dynamic methods. Static flexible interconnection is just sort of changing the input assumptions that planning uses and sort of how the resource behaves. So it's more complicated, but it's still basically a set it and forget it that operations doesn't care about. But dynamic flexible interconnection is the big sort of curveball. And this allows operators to physically set like load or DER, like maximum real power input or output points in real time as grid needs change. So instead of like making a system upgrade to prevent any bad thing from happening that may only happen like 5 to 10 hours out of the year, the idea with flexible interconnection, especially dynamic, is you would send a signal to reduce the level of like consumption or to reduce the level of like solar production during these specific hours where things are constrained. There's a lot going on under the hood to get this to actually function and to be sort of serviceable for both parties, but it is a very interesting concept that is hopefully driving improvements and less construction and more sort of flexibility in the operating space. There's a lot there. I'll refer you to the Charged Initiative document that's linked here. There's a lot of really, really good material in there that goes through the details of what this actually is and how it works and what the methods are. But for our purposes today, we're kind of just driving operations and planning together in a way that is good, but making things more complicated. Resiliency planning is another one. This is really pulling from almost like a wide variety of different departments. You've got planning engineers in here, you've got reliability, you've got designers, and you've got system operators. So first, I think it's useful to define what we mean. When we say reliability and resiliency. Reliability is like your normal things that you expect to happen on a daily basis. So trees, cars hitting poles, regular storms, squirrels, cable faults, etc., all falls under reliability. Resiliency, in contrast, is the ability to sort of withstand, recover from, or reduce how bad really disruptive events are. These are your hurricanes, big heat waves like winter storm, snowpocalypse, snowmageddon. type of scenarios fall under resiliency. This includes a couple, like resiliency planning is just sort of making yourself ready and assessing your capabilities and anticipating how these things are going to impact your system and sort of doing some make ready ahead of time. So things like a vulnerability assessment, restoration planning, grid hardening, like operate, like where your operator is going to be, how are you going to keep your dispatch building powered? What happens if we don't have enough generation and we have to shed load? Like all of these different aspects. And the NARUC resilience framework does a really great job of going through a lot of this. But generally, we're talking about or anticipate that it's coming, withstand it when it happens, adapt to minimize the impacts, and recover. And resiliency investments can benefit you across one or all of those different aspects. I also want to highlight this upcoming NISUCA report and just sort of talk through how integrating resilience planning with distribution planning works and is beneficial. So I mentioned we're sort of bringing things closer together. Um, there are a couple different avenues where this sort of happens and makes the most sense. In like state integrated distribution plans are often bringing in resiliency as an aspect of considering different types of investment, different like enhancing reliability analysis when you're sort of considering the value of different types of investments like new substations or reconductoring or undergrounding. You're trying to capture that additional resiliency that might come from those in your decision making. You're also looking at like root cause analysis and like worst performing circuits. Um, Historical data is oftentimes hard to do with resiliency because it's hard to get good records for all the extreme events that might happen, but there is some good stuff hidden in there that you can kind of identify from like previous events and sort of draw forward from. And then the last piece, just incorporating long-term resiliency planning into distribution system plans. So things like design standards are a major in here. For instance, like I'm familiar with, we started using a stronger type of pole every fourth pole on our subtransmission system when I was at Ameren to help prevent cascading, right? Like these sorts of long-term like investment standard practices that drive some increase in cost, but improve that resiliency are showing up more and more in distribution system plans. The last topic we'll talk about is proactive investment, which is sort of the intersection of planning with customer service. Historically, distribution capacity investments aren't really executed until there's pretty high certainty that there is a specific need. So this is either like short-term load growth anticipated because of like new projects, new development, new subdivisions, or like specific large load customers coming in at the multiple megawatts level that you know you're going to need capacity there as a result. Because you're waiting historically until there is really high certainty that that's the right investment and that you need to make it, there can be delays because it takes a long time to build distribution infrastructure. Relatively speaking, like we're on like the like 1 to 3 to 5 year time frame. Um, Transmission folks will laugh at me when I say it takes a while to build because that's much faster than building new transmission is ever going to happen. But if you're a customer trying to interconnect a new EV charging station and you get told 2 years, it doesn't seem very fast to them. So that's sort of the idea with proactive investment is we're building out further in advance of the need when those needs are relatively less certain to improve the customer experience or long run efficiency or to help sort of improve the speed so that we can meet state energy goals. There are a lot of sort of trade-offs between the current practices and like this sort of proactive approach. The biggest difference is we're trading off this risk of negative customer experience against a risk that we don't make the right investment at the right place at the right time. So there, again, there's some really good material from Charged that I've got linked here that explores this in a lot more detail. But that's really the crux of it is sort of considering the customer impacts of not having enough capacity when we need it and driving decisions as a result of that. All right, so that covers everything I had planned for today. I'd love to open it up and see if we have any other questions.
While people are waiting, I have a question. While
Sure.
people are thinking of their questions. I wanted to, you got into this a little bit in the breaking down silos slide, but I wanted to ask you more about how do you see distribution system plans addressing operations issues? Like certainly asset management front and center, as part of a distribution plan, but what about the other aspects of
That's
operations?
a
How do they blend in?
that's a really good question. System operations doesn't really get talked about a lot in some of the plans, other than to say that they exist. A lot of times they end up on the receiving end of whatever everybody else decides to do and build and how to operate. I think that's changing a little bit, but they sort of still see their role as like a safety and outage restoration role. And that structurally hasn't changed a lot, even as some of these new responsibilities have come in. A lot of the new stuff is automated in a way that there's like a new team in operations overseeing it, or they're sort of trained on how to interact with it. Um, I think there's room for a lot more focus on like system operators in some of the DSPs, especially as things get more complicated. It's going to become like a training issue. And like at a certain point, we can't just keep adding new systems without engaging with the operators themselves and be like, oh, don't worry, it's going to happen automatically. Like they need to be prepared for what happens when stuff goes wrong. And the more automated systems that we have, the more preparation that they need to have to sort of manage all of those effectively. So I think there's sort of some what if, oh snap, bad things are happening. What do we do? That sort of needs to be talked about a little bit more in there.
Okay. So when I think about like buckets like, capacity expansion, like as one big bucket for distribution planning and another bucket where we're shoving together maybe, asset management with reliability and resilience sort of planning, right? For the existing system, looking at the existing system and then what mods you have to make for that. So I just, um, your focus was good. Your focus was on like the operators, getting them engaged because they're going to have to deal with this. But how would you, as as a best practice utility, what would you put in the plan that would more thoroughly address operations
I
writ
think
large?
one element that I haven't seen talked about as much as I think it could be is the role of like trouble trucks in speeding up outage restoration. Like those, that is the person who is out there responsible for getting stuff turned back on. So making their job easier, giving them more tools, giving them more ability to patrol better and faster, things like fault indicators, things like fault location technologies that sort of predict where faults might have happened. Generally, you're patrolling pretty wide areas. I used to be a drone pilot. We had some devices that when a fuse blows, I've got like 7 miles of line to run down to try to find one squirrel, right? So speeding up that detection process, like segmentation, like that piece of it, getting more tools for like operations, especially like trouble trucks, can really impact your reliability statistics in a way that doesn't show up with like asset health investments or other sorts of things. Like there's a human element in there that I think is still important, and not just because my dad was a troubleman.
That's great. I love that. There's a question in the chat. There seems to be general discussion about how electricity is becoming more diversified, particularly if more customers install energy infrastructure, batteries, solar, natural gas generators, whatever. How do you think this will affect the perspective of traditional distribution planning? Might there be a need for distributors and perhaps even non-utility distributors to expand their planning and operations?
Oh yeah, you have hit on the central crux of distribution planning in 2026 and the arguments I have with lots of my colleagues. What is the role of DER and these sorts of new resources? How do we treat them? Are they positive? Should we assume they're never going to be there when we need them? Do they actually have positive benefits? What are the interconnection challenges? How do we connect as much of them as possible? Like all of those are all swirling around, and lots of utilities and planners have found very different sort of like stable places to argue from in that space. I think there is more and more coordination and more stakeholder engagement every day in these areas for like between developers, third parties, like resource owners, folks that run these types of platform, like VPP style platforms. Um, there's a ton of opportunity in distribution for like flexibility and customer-sided resources to come in and add value and relieve congestion and constraints and avoid triggering some of these big multi-million dollar upgrades. A lot of that hasn't really been realized yet because those conversations are still pretty nascent. So there's a lot of push towards like using customer-sided resources for distribution services. We've got a ways to go before we get there, but that is a like going to be the big crux of distribution planning and how it evolves over the next like hopefully couple of years, but more realistically probably at least like 5 to 10 years.
That's great. And they're on that last topic, Cody and everyone here. April 21st, we'll have Paul DiMartini up, and he's really gotten into the weeds on how we have to set up, or how we can set up distributed energy resources to actually contribute to solving grid needs rather than maybe considering them an issue or a problem. We have another question. Can you speak to end use energy efficiency as a resource for addressing distribution capacity constraints? Is this a realistic approach to make the most of the existing distribution systems and avoid costly system upgrades? What would it take operationally?
Yes, this is a great question. I am a little bit of an oddball in the distribution planning field because I think energy efficiency can be really impactful to these and has been. I think it's just not been sort of talked about in some of the forecasts because we saw load growth just like flatten out entirely, almost not almost entirely, but like with a major portion of that being because of things like energy efficiency, heat pumps, LEDs, etc. From my perspective as a solution, it's hard to be out in front of because a lot of times like planners historically have not looked out that far ahead because they're like, oh, how do I get through the next 2 years? Because it takes me 2 years to build a mitigation project. 2 years is not enough time to get enough energy efficiency to avoid a specific upgrade. So it tends to get kind of like pushed off to the side of the solutions pile. But like when I've talked to some of the energy efficiency folks where I used to work and been like, look, this entire like section of like 6 substations in the city of like O'Fallon, Illinois, I am running out of capacity everywhere over the next 10 years. If you can get as much energy efficiency in the city of O'Fallon as possible, that would be great for me and not having to build stuff. And those types of conversations are really easy to have. So I think it's challenging from a specific sort of analytical perspective because it's like, well, you're never going to defer a substation with 7 light bulbs. But like if you start early enough and like sort of target some of the incentives to areas where you know you're going to have problems or you know this growth is coming, right? You can get out in front of a lot of that and really recognize that value.
Yeah, and actually, the findings I think are that it's easier to do sort of programmatic distributed energy resources as non-wire solutions compared to the solicitations or requests for proposals that have been done for a long time. First of all, utilities already have money, or their third-party administrators already have funds for these things. So if you can get extra value by targeting the investments to specific locations on the distribution grid, or providing perhaps extra incentives to recognize that extra value. I'm
Yeah,
glad.
I think either increasing the level of funding in some of these areas that have like specific or like that have broad growth needs is a huge area to potentially improve outcomes in that doesn't take as much structural change as some of the other ways of doing procurement.
I just put in the chat a link to a presentation we did a couple of years ago for ACEEE that summarized at that time some of the ways that energy efficiency was participating um, to help the distribution system. What other questions do we have? Or any comments that people want to offer? I mean, Cody is a font of information. Usually when we do distribution trainings, everybody sort of gathers at Cody's area to ask questions. It's harder virtually. The question is, are you open to be in contact in the future if anything comes up?
Certainly, I love doing distribution stuff. I've been embedded in it my whole life. My dad was a lineman, and storms paid for like every nice thing in our house. And then I went into a co-op at the utility and have been working in power systems my whole career. So if anything comes up that's of interest, feel free to reach out. I'm happy to just answer questions or just kind of talk about like problems and solutions.
Thanks so much, Cody. I put Cody's contact email in the chat. Sure. This is a career-related question. What would your recommendation be for those who want to explore working and developing in this particular field? And they didn't necessarily have a father who was working at the utility.
That's a good question. There's almost no substitute for utility experience in distribution because the accessibility of the material is so much lower. Like power systems courses in universities do a great job of teaching you about transmission and generation, but like the distribution pieces that they're talking about are either like older or assuming things we don't have or assuming like knowledge and technologies that are too expensive or like assume a balanced three-phase system. And it's like, no, we can't do that. So finding ways to get exposure and review like actual practices and standards and terminology is really, really, really important. Doesn't have to be working at the utility. There are different ways to do this with like all the integrated distribution plans that are out there. Are really great resources for this because you can read about how it all actually works and go like, oh, okay, it works like this, and this utility is doing thing A with capacity planning, and this utility is doing something else, right? You can sort of pull from that material and learn how it works. Nothing in distribution is that complicated, but there's like 10,000 little rabbit holes to go down, and then they all pull back and interact with each other. So just looking at like existing materials and practices and critiques of those practices and materials can teach you a lot about what's going on and how it works. That would be my sort of best place to start is read those plans. If you want to sit down for a couple days and just read hundreds and hundreds of pages of technical documents, that turns out to be probably the best way you can do it.
Thanks, Cody. So I just put in the chat a couple links. The first one is to our online catalog of it's both state practices or requirements or guidance, as well as filed utility plans. And we are updating that now by the end of May for sure. The update will be completed. Meantime, got everything updated as of a year ago. So that's the first link. And the second one is just our distribution planning page, where there's a wealth of information, including trainings that Cody and others have given for Berkeley Lab and publications.
Yeah, those are probably a better place to start, just to get like exposure to concepts, and then like further reading and research in the integrated planning space. But Berkeley Lab has a ton of great materials and trainings and papers that explore a lot of these areas from a holistic perspective, which I think is important.
Great. Thanks, Cody. This has been so great. Thanks to everybody who's joined us today. We'll be posting the recording and slides the slides are posted in the same link. We'll also have the recording shortly. All right. Thanks so much. Have a good day.
Thanks, everybody.
Bye.